So welcome back to the next problem, guys. This problem will be from heat exchangers, which is the last part of your unit 3. So it's a very important section in which at least one question is definitely expected. So now we have a counterflow double pipe heat exchanger here. So we have a heat exchanger here in which water is heated from 25 to 65 degrees Celsius by using an oil with specific heat 1.45 kilojoules per kg Kelvin and a mass flow rate of 0.9 kg per second. So this oil is cooled from 230 degrees Celsius to 160 degrees Celsius. Because of heating this water from 25 to 65, eventually the oil will get cooled. So if the overall heat transfer coefficient is 420 watts per meter square, so you should calculate the following: the rate of heat transfer, which is Q, the mass flow rate of the water m dot, the surface area of the heat exchanger A. So as far as this counterflow double pipe heat exchanger is concerned, you will have two pipes in which water is flowing in pipe 1 and oil is flowing through another pipe. So both of them is going to flow in opposite directions, and that's why you have the term counter here. So water will be heated from 25 to 65 as a result of a hot oil flowing in the opposite direction. It gets cooled to 160 degrees Celsius from 230 degrees Celsius. So let's now solve this problem. So we have a hot fluid which is oil. So remember, it has to be written as T1 and a T2, and we have a cold fluid which is water, and the terminology here is we have to use small case T's, T1 and T2. So here T1, entry temperature of oil, it is given in the problem as 230 degrees Celsius, and its exit temperature is 160 degrees Celsius. So this is T1 and this is T2. Similarly, for water, entry temperature of water is 25 degrees Celsius, which is T1, and exit temperature of water is 65 degrees Celsius, which is T2. So, and the overall heat transfer coefficient is given as U is equal to 420 watt per meter square. So now we have to find the rate of heat transfer, which is Q, the mass flow rate, which is m dot, and the surface area of the heat exchanger area A. Alright, so now we all know heat transfer Q has three relations. The first one is m dot into h of g, and the another one is UA delta Tm, and there is another one which is HA delta T, and here the most popular one, MCP delta T, which you would have learnt it in your physics. So this is your MCP delta T. H denotes the hot fluid, and this is the mass flow rate of the hot fluid, and this is the specific heat capacity of the hot fluid. here you should see that, you should note that the mass flow rate of the hot fluid is, the hot fluid here is oil, so 9, and the specific heat capacity of the hot fluid is, so the oil is the hot fluid, so specific heat capacity is 1.45 into 10 power 3. Do not substitute in kilojoules, so make sure you substitute in joules, and then the temperature difference 230 minus 160. So this will be 91.35 into 10 power 3 watts. So you have found out the heat transfer Q. So now you have this formula Q is equal to UA delta Tm, which we have discussed in the class about this logarithmic mean temperature difference. So the value of this delta, the relation for this delta Tm, which is called in other words LMTD, can be obtained from the HMT data book, page number 151. So this will be your relation. So from this relation, for counterflow, delta Tm is given as T1 minus T2 minus T2 minus of T1 minus T2 divided by T2 minus T1. So this relation is available in your HMT data book, page number 151, for counterflow heat exchanger. Okay, so now T1 is 230 minus 65 minus 160 minus 25 divided by natural logarithm of 230 minus 65 divided by 160 minus 20. So now we have this delta Tm as 149.49 degrees Celsius. So this is your logarithmic mean temperature difference value. So now you look at this relation here. We have the value of Q, we have the value of U given in the problem, we have the value of delta Tm. So from this you can easily find out area. So I will substitute this delta Tm value here. Q is equal to UA delta Tm. Q will be 91.35 into 10 power 3, which is equal to 420 into area into 149.49. So now you will get area as 1.455 meter square. So this is how you find the area. Alright, so now for cold fluid, TPC T2 minus T1. So please note the change in the signs here. So T2 will come first for cold fluid always. So m dot C, the cold fluid is here water. So it is given in the problem as I don't think it is given in the problem. You have to find it out, the mass flow rate of water. So m dot C, Q is we know already, which is 91.35 into 10 power 3. So specific heat capacity of water, you can easily remember this is a standard value 4186 joule per kg Kelvin. This is a standard value, so you have to remember this value, or you can find it even from the data book, specific heat capacity of water. Okay, so now T2 minus T1 is 65 minus 25. So now you will get the mass flow rate of cold water or the cold fluid here is 0.545 kg per second.